let me just run through the committee first. I am the chair of this committee, so formally, so here I am. And then internal members are Vignesh Narayanan and Amitabh Das. I see Amitabh Das there. Let's see if Vignesh is there too. Yes, Dr. Narayanan is there too. So Dr. Das and Narayanan are here. And I see Alessandro Oltramari, Alessandro Oltramari, the external member from Bosch Research Institute, the president of Bosch Research Institute. Buongiorno, Alessandro. I hope you don't mind if I say good day in Italian to you. Buongiorno.
Buongiorno, I don't mind, yes.
So all of us are here, and I see there is a pretty robust attendance from non-committee members, which is welcome. So a small reminder, formally, this is also, of course, the proposal presentation, but it is also the comprehensive exam for Mr. Roy. Not the qualifier, that's a different story. So typically we concentrate on the proposal, but the committee members may feel free, should feel free to ask broader questions if they want to assess that the candidate is prepared to complete the dissertation. So this said, I guess we'll have, as usual, questions of detail during the brief questions of detail only during the presentation, and leave the major questions at the end. First, the audience will be allowed to ask questions if the committee agrees. This is a proposal, not a defense, so that's not necessary, but I think it may be a good thing to have a broader discussion at the end. And then the committee will just meet with the candidate, and then they'll deliberate separately without the candidate. Okay, so that's the schedule. Let us, Mr. Roy, Kaushik, please start. And do you have a time frame in mind for your proposal presentation? I noticed it's rather short, like 16 slides, but there is a lot behind each slide. I know.
I'm assuming it should be about 45 minutes to an hour.
Very good. That 45 minutes to an hour will be typical for this. So please go ahead. And if Dr. Sheth agrees in particular, no, are you okay? Okay, go ahead. Go ahead, Mr. Roy.
Okay, good morning, everyone. Thanks for attending my talk on my PhD proposal topic, which is process-grounded neurosymbolic AI. The structure of it is going to be a why, what, how format. Before that, I'd like to thank in advance my committee members, the main chair, Dr. Valtorta, Dr. Narayanan, who has been a very close collaborator of mine, Dr. Das, Dr. Ultramari from Bosch, and of course, my advisor, Dr. Shet. So this is a kind of rough outline. I'll start with a motivating example, and then that is going to be a toy example. Then I will transition to a motivating example with more realistic consequences. Then I'll go into the proposal statement. What is the statement exactly? The prior work, 4 perspectives on it and identifying gaps. Then I will cover what is the formulation and what is the problem statement objectives and what are the expected outcomes. I'll also have examples in there for enhanced clarity. And finally, in the how part, that will encompass select papers, publications from my work. And I'll also do my best to sort of provide a bird's eye view of all the work that I've done so far. And I'll end with what's remaining for the remainder of my PhD. So the motivating example. Let's imagine a seemingly mundane task. Find me an ice cream shop within 30 minutes of me that serves vegan ice cream. So this output on the left-hand side was obtained using the most state-of-the-art and most popular uh, agentic AI-based software. It's called AutoGen from Microsoft. And so what AutoGen does is when you give it a task description like this, it goes off in the backend and spawns multiple agents, as many as it deems necessary, and provides a task resolution. So as we can see here, the first agent is tasked with mapping the locality, which is get ice cream shops near this location. And we make certain assumptions that it has access to my location and so on. The agent 2 then obtains relevant information such as what's on the menu for these ice cream shops nearby. Agent 3 sifts through the menu to find vegan options, and Agent 4 finally consolidates all that information into actually providing me an establishment to go to. Now, a couple of things that it did not check that humans might have, probably would, is that establishment even open? Um, are there special hours today because it's a holiday or something of that nature? So that's the apparent issue with this sort of autogen approach. And then also we don't understand its mechanism because these are all black box LLMs. And those are other algorithmic issues. So in summary, there are no sanity checks and there's no clear way to understand the robustness in the mechanism. Contrast that with if you had provided some knowledge, process knowledge based scaffolding. So when I say process knowledge, I mean what is the procedure to solve this task. At the very minimum, check the operational status of all these establishments near the location, meaning are they open or closed, before you take the pain of going through this multi-agentic complicated decision process, right? So uh, that's this motivation for using a toy example. Why is my work important, and why is it important, especially in today's context of AI? Um, so that's a toy example, but what if that kind of mistake happened in a real world medical scenario? So here is a plan that a medical expert is carrying out for a patient in diagnosing them for a certain illness, in this case, depression. So they take the patient data, they map it to a checklist of 9 symptoms. This is written in their textbook material. They tally up the scores on those symptoms, and then they make a recommendation based on the score that's obtained. And they sometimes add context if necessary. For instance, if the score generated is in the 10 to 14 category, here you find that the proposed treatment action is pharmacotherapy, that means medicine, or CBT, which is cognitive behavioral therapy. That's an advanced form of therapy. But let's imagine that the additional context is the patient is carrying a child. Then we want to make sure also that the medication is not interfering with that, right? So a real world process is quite complicated, and letting a framework like AutoGen fly off without any guidance and try to provide a task resolution is dangerous, and also has very high likelihood of being inaccurate. Okay, so this is the statement that infusing process knowledge into AI systems is crucial. By grounding learning and reasoning in expert-defined process structures, we can achieve not only high accuracy, predictive accuracy, but we also dramatically improve the explainability and safety of the system. Okay. Now, I'm going to cover 4 perspectives on what has been done in prior work with regard to process modeling. So the first perspective is titled explicit process modeling. So this is from more classical AI days, where processes, are also at that time known as workflows, uh, were modeled by hand pretty much, and by engineering, by extensive domain engineering. So within that, the first category is classical planning. In classical planning, you had explicit multi-step plans defined based on a domain model. There were mostly deterministic actions with well-defined preconditions and post-condition effects, and then a well-defined state description. So once you went through the engineering effort to specify all of that, your automated planner could go off and find you a task solution based on your defined optimality criteria. Um, A similar but a different knowledge representation based approach is workflow engines. So the representation in classical planning is typically something called PDDL, Planning Domain Description Language. In workflow, they chose a different language called Business Process Management Language, BPMN. And then the flow diagrams were depicted as flow charts. There was orchestration similar to you might have in planning, and there was a rigid process defined, just the same as you would define a domain model. The rigid process.
Mr. Roy, kindly repeat what the abbreviation BPMN stand for.
Business Process Management Language.
Thank you.
Yes. So in a business process, also what needs to be defined is how do you handle exceptions. So you would siphon off an exceptional case to a human operator, for instance. So this was more tailored for actual enterprise business processes compared to more academic domains in classical planning. Then in the big data era, we moved on to data-driven methods such as decision trees, which you can read a decision tree fairly easily. It's quite interpretable as a structure. But you can also obtain the decision tree through inductive learning from observational data. So that's an advantage that became a significant advantage because there was vast amounts of data available in the big data era. In decision trees, you had fixed interpretable decision paths and flows. And after decision trees, you had more nonlinear process mining methods. Decision trees you can actually write out as a linear function. And those methods, they work towards discovering workflows from whatever data is available, for example, process logs. And you can do offline analytics to figure out what specific aspects of the discovery process would you like to optimize further. Much later on, you were able to exploit advanced statistical methods, for example, reinforcement learning, which has pretty sophisticated algorithms. Recently, the founders, you might say, or the fathers of reinforcement learning, they won the Turing Award, I think a couple of days ago, Sutton and Bartow. So this is now also a very popular field. In reinforcement learning, plans are called policies. They can be linear, nonlinear, multi-step in structure. You had a temporal abstraction, so it's a sequential decision-making process. And then you can have adaptive learning. So the learning procedures are amenable to quick updates. So here I've put a representative list of references, by no means exhaustive, but these are some of the seminal references in these works. But now, what are the open questions? If you look at each of these 5 categories, there's not a general pattern emerging. There's no insight into what's a optimal knowledge representation framework that's common across all of them. And so when you're trying to adapt this for, let's say, the modern AI context, which one or what subset of these should you pick? And then how does that impact scale? Can you leverage modern language model-based tooling in doing that? What's now known as a neurosymbolic approach. So these are the open questions. This is the second perspective on prior work, which is split into 2 parts, multi-stage reasoning approaches and single-step decision-making approaches. So in multi-stage reasoning approaches, the classic is Daniel Kahneman's Thinking Fast and Slow, where he explicitly laid out 2 different systems, one for deliberative reasoning and one for more reflexive pattern matching based reasoning. And more recently, you have language models trying to mimic certain reasoning behaviors through explicit prompting based approaches where the prompt clarifies that elucidate your chain of thought when coming up with your final answer. There are many variations of chain of thought today, but the 2022 paper was the first one. The other approach is a single step decision making where you have a large monolithic architecture, typically a large neural network. And the assumption is that there's some reasoning that happens within the internal parametric layers, and the answer is conformant with any reasonable plan that you might imagine for this task. Of course, this is a black box, but you get an immediate decision. It's trained to follow decision processes um, in a particular domain. So again, that assumption is based off of that training. Um, so what we would like to do is have a hybrid approach. So let's take the example of driving. You might have a complex situation where you have to do route planning with a traffic accident that spontaneously occurred. So in that case, maybe you invoke a multi-stage reasoning chain of thought procedure. On the other hand, most driving behaviors are reflexive pattern matching based. So we would like a approach that intelligently selects between the two. That's the open question in this perspective. Um, the levels, this new perspective is on the levels of process formalization, which spans rigid rule-based approaches to their more stochastic varieties, so probabilistic graphical models, to more recent function approximation based, which is neural networks, and finally, neurosymbolic approaches. Here, the main challenge is what's the sweet spot between rigid structure and flexibility attained through um, function approximation? And then when I say sweet spot, what's the correct balance of logical expressivity and data-driven scalability and flexibility? Okay. Now, the last part is about integrating process knowledge into learning. If you have a learning system, which is usually based on differential calculus, you have on one hand a fundamentally discrete structure in logic and its varieties, and on the other hand, continuous space optimization in differential learning based algorithms. So this hybridization is a unnatural fit, but we'll have to synergistically leverage both the strengths and leave out their weaknesses. So how do we do that? Some seminal works in this regard is AlphaGo and Alpha many things after that, like AlphaFold and stuff like that from Google DeepMind, which showed that for a particular domain, if your domain axioms are clear, you can get significant gains by employing a neurosymbolic approach. In fact, the founder of AlphaFold won the Nobel Prize for chemistry this last year. So it's that important and that effective. Right? Okay. So now contrasting all of that against what I'm proposing. So you have to fix the rigid, inflexible nature of classical AI, the opaque black box nature of modern LLM-based systems or neural network-based systems in general. And then something I'm calling conversion bottlenecks, which means should you choose predicate logic, first-order logic, knowledge graphs, what kind of formalism to scale properly and hybridize properly with neural network architectures. To achieve what? To achieve multi-stage reasoning and appropriate knowledge infusion, flexible formalization. Can you specify things partially? Do you need to lay out everything explicitly and so on? Neural and symbolic integration, and then benefits for the end user, explainability, interpretability, accuracy, safety, and scalability. Okay, that's the why part. Now I come to the what part. What's the problem? This is mostly going to sound like a recap. So many AI systems are black boxes today, and they lack explainability and control. So especially in high-stakes tasks, such as medical diagnosis, that's the problem. So the objective is to integrate process knowledge to alleviate some of those issues. The impact is going to be apparent not just in the medical domain, although majority of my work is in the medical domain, but across tasks with mission critical characteristics. So once again, to recap, the kind of task that I'm going to show demonstrations of is the medical diagnostic and recommendation task. The summary of advantages would then be you would have in some form an explicit representation of the process divided into clear stages. Tractable integration of neural and symbolic parts. When I say tractable, I mean it runs in a reasonable amount of time, algorithmically speaking, but also is accurate. The quality of the output is not compromised. Safety and explainability. The process is entirely transparent. You can check it for how it's making its decision support. It's not entirely transparent, but it's transparent to an adequate degree. Um, and then explainability means the outputs are cast into a format that the end user does not have to spend much effort in interpreting it for their use case. And finally, flexibility. So you can have all manner of complex workflows implemented using this method if successfully implemented. Now here is some notation just for clarity of exposition later on. Um, we'll call the inputs X, the outputs Y, where X is, when we go back to the figure, the patient data, and the output might be explained recommendation if this is a 3-stage process, making the recommendation if it's a 2-stage process, and mapping the data alone if it's a 1-stage process. The process knowledge itself, which is a set of conditions, which may or may not have Boolean values, but in my work, it has Boolean discrete values. It can have multi-category discrete values. Some sort of mapping architecture available to us that takes the data in X and is able to map it to the conditions in the process knowledge. A decision function, linear or nonlinear, that applies on that mapping and produces a final output Y. So key scenarios that I will cover is categorical decision making. Is the person depressed or not, and what degree of depression do they have? A natural language explanation generation, verbose verbalization of what's going on with the patient, and multi-stage processes, which is diagnostic assessment the end of it, or do you want to move on to recommendation and then explanation and so on? Okay, here is an example illustration of how the notation maps to the running example. So I mentioned you had the patient data as X, the process knowledge as C, the conditions. This embedding model is an example of a mapping available to us, the H, that takes the X and maps it to one of the conditions. And then the phi unspecified here is a nonlinear function applied to the mapping that results in the final diagnosis or explanation, depending on what we need. Okay. That covers the what is a process knowledge infused learning part. Now I'll come to the how, and I'll cover the how through a series of publications. There were a couple of representative publications that occurred before LLMs became popular and more broadly accessible in 2023. And then the remainder of the work is after that. So first, we'll start with the work before LLMs. In the first method, again, recapping the notation, the embedding model is a sentence transformer. So what a sentence transformer is it's based on the transformer neural network architecture. And it's called a sentence transformer is because it takes any arbitrary English sentence and maps it to an abstract vector space. So you get a vector out of it. And then the way that you would map the patient's data to one of the 9 checklist items is you would chunk the patient data into sentences and then take each sentence, vectorize it using the embedding method, take each item on the checklist, vectorize it using the embedding method, compare the two using a similarity metric, and if the similarity exceeds a threshold, then you have a viable mapping.
There's a question you want to quickly address, and
Yeah.
Hi, Kaushik. This is just a quick question regarding the explanation generation, the natural language explanation that you're generating. Who is the intended user of the who's going to be reading? Is it the patient or is it the clinician who's diagnosing the patient? For which user is that intended?
That's a good question. So the explanation in many of the implementations that I have worked with is for the domain expert. You'll see that there is a view that the patient has, and that's also natural language based. But the reason that I can't speak too much about that is there's no objective evaluation criteria for that. I can say that the explanation for the expert is reasonable because you can map it to things that they would expect in a reasonable explanation. For an end user, it's very subjective. So you'll see that there is a natural language output for the end user, but I don't have numbers on is that a good output or bad output beyond they're happy with what they're seeing.
Okay, thank you.
Yeah. So yeah, in the first method, I covered the embedding method. It's a sentence transformer based thing. So then the neural mapping involves invoking that sentence transformer to map pieces of the text to the checklist, the H function. And there are m equals 9 here. There are 9 items in the checklist. Your decision function in this case is linear, meaning you just tally up the scores. And if it's within the 0 to 4 range, you get none. None actually doesn't mean none. It just means continue counseling. 5 to 9 is mild, which means you pay a little more attention and then follow up as necessary. And 10 to 14 is considered a clinical case where you have to then go to a doctor's office, get CBT, pharmacotherapy, possibly any other detail that is specific to your circumstance. Um, and the output is a text-based explanation. And sometimes it ends at recommendation. So you'll see examples of both. So what are the baselines? So this is just about the time ChatGPT came out, but baseline one is BERT based. So BERT is a bidirectional encoder model, which is before ChatGPT, it was a very popular language model architecture. Um, what you do is you take the input text, you pass it through BERT, and then you do BERT's internal parameter space visualization. So what that results in is these yellow highlights. Then you compare those yellow highlights with the doctor's definition of depression, which means the reason for doing that is the doctor should be able to interpret the output of the neural network, both the prediction output, the quantification of it, the 0.99 score, for instance, and the highlights. Now, the doctor, when they see these outputs, there's at least in most cases, there are some cases where the highlights match with parts of the definition, but in most cases, it's a very heavy lift to take these highlights and then map it to sections of the definition. That's the first issue. I don't think it's that I don't care anymore. It's hard to map that to any part of this definition. And hang in there and hoping this cloud over my head will pass is again hard to pass. The criteria is extremely well defined. There are daily activities that they are not able to engage in. And then their depression symptoms must persistently last for greater than 2 weeks. None of that is clear from these highlights. The second issue is that you have a number 0.99. So I'm happy to discuss the details if you want to know more, but for right now, the TLDR of it is these numbers are always high. Neural networks always are confident in their outputs. That is an artifact of their loss landscape. It's a problem that is called measure concentration. So you can't really distinguish one number from another, even though in the neural networks, highly zoomed in space, it knows the difference between 0.99 and 0.989. But the doctor does not know that, right? So from the doctor's point of view, a confidence like 0.99 means everybody gets medication, right? Even if you try to recalibrate it to the 0 to 14 score. So that's baseline number one. Baseline 2 is ChatGPT. At this time, it had just come out. You take the input text, you prompt ChatGPT to tell you the depression analysis in this text. And then the quantification is still some model based. That's not ChatGPT. And the highlights is again model based. But this time we find more highlights. So the highlights are obtained using a method called integrated gradients. So that means if you perturb the vector values for each of those chunks, then the output changes significantly. And so it seems that more highlights correspond to significant perturbations in this case compared to baseline one. So ChatGPT's outputs are more information rich in that regard. Here, information is in the statistical sense. Um, so still, we have the same issues as last time, that the doctor does not know how to clearly map this to um, the symptoms. I mean, the characteristics that they require to assess depression. The score again doesn't mean much. But
What if I were to give very detailed prompt going by each of the PSQ questions and ask the analysis for each of the PSQ question with the vocabulary that is relevant to each of the PSQ question, PSQ?
yeah, so that's a good question. So we've done that work this year, and uh, across a whole bunch of language models, and the latest ones, Llama and Mistral and OpenAI and Grok based services. And the results are, we have preliminary results. It's under review at ACM transactions, and we'll find out how it does. But my hunch is based on preliminary observations that you can get much better outputs by doing that. But the challenge lies in uh, minor things like how do you even capture the response, because it's one long string. How do you take the elements of that string and give it to that doctor without them looking at it? It sometimes writes surrounding text that is irrelevant. Those are minor syntactic things, but more semantic things are sometimes the mappings are plain wrong, um, as you can see through the ground truth. But the objective results on that will come out, and we'll have a look at it. Okay. So what's our method? Our method is the mathematics of it is basically you stitch together these parts in one end-to-end differentiable loss function, and then you backpropagate through it. And when you do that, the outcome is reflected in the parameters of every intermediate stage. And so you get only the outputs that are relevant to the elements in the definition or the items on the checklist. So then you find in your ontology mapping neural network, the daily activities is identified. And in your symptom mapping or criteria mapping neural network, you find hot minute, which is at the Urban Dictionary term for more than for several weeks. So in this case, interpreted as 2 weeks. Then you find items in the checklist, 1 to 9, such a little interest or pleasure in doing things, which maps to a direct phrase in the input text. And so now you can apply the tally mechanism, you can give it a severity label, you can propose treatment actions, and then provide it to the expert. Now the expert has to do minimal lift to interpret this result. They can check it because it's decomposed into stages. They can check that hot minute refers actually to more than 2 weeks and so on. But the point is that the quality of output is much better for them to actually do something with it. Right. This is a second application scenario, which is suicide related. So similar to the depression case, there's a nonlinear checklist here, a flowchart type of decision process for determining suicide severity. And the process is similar. You take a model and you map it to elements of this flowchart, and then you provide that flowchart to the expert for their final assessment. So the qualitative evaluation results are with the best baseline at the time, it was Da Vinci. I don't know if you remember that model. The experts agreed with the output 47% of the times, and with our method 70% of the times. The remaining 30% is when things are unclear in the text itself, or when the sentence transformer based mapping threshold needs further fine tuning. And usually that happens around people expressing their symptoms in using sarcasm or jest or things like that. A gamer saying that I want to do extreme things is interpreted as an actual clinical symptom, for instance. So those are the remaining 30% cases. Okay. Now method 2 is a text generation case. So what's the problem? That you're engaged in a query session with a model, and you provide a query, and the model has to now provide to the expert a set of possible next questions to ask, follow-up questions. Here, the generative model is transformer based, and a transformer, I mentioned earlier, is a large neural network, and the output of a transformer is a probability distribution over next tokens. A token is one unit of a sentence. You can think of it as a word for simplicity. So then you have that to work with, language model probability, and then you can modify that probability using three things as we have. One is a ranking heuristic, which is a ranked list of ground truth questions given to us by the domain expert. This is a domain expert from Medical University of South Carolina in the psychiatry department. And then you can check it against contents of a knowledge base that's available, for instance, UMLS for clinical items. And then you have, once again, a safety lexicon. This is provided to us by the domain expert. This is actually an unsafe lexicon, meaning words you shouldn't say. And so you can take into account these three items and modify the language model probabilities. So this is the baseline, GPT-2 at the time. These are the items that GPT-2 produces. Now, admittedly, this output is termed as risky by the domain experts. There were two of them. There's no quantitative measure to term this as risky as of yet. But they told us explicitly why they think it's risky. So they would never use words like self-destructive and extreme in their discourse with any patient. So they include that in their unsafe lexicon. And then when you run it through the math that I showed, you get modified questions accordingly, right? And so that's the main idea in this approach. And you run this through a bunch of queries and record the results. And these are the results. For any baseline, all baselines in this are transformer based. We get significant improvements using this modification procedure. Significant improvement in this expert satisfaction. Okay, so that's before language models. There are a couple of publications after language models became a thing. The publication number 4 here is just a preprint. It's not yet published. This is related to what Dr. Shet asked earlier, that when you state in the prompt, map things to a checklist, map things to certain recommendation procedures, does it do better? So this is a journal paper. It's 25 pages long. We have surveyed a whole bunch of models in their ability to do this. And we have preliminary results I'll present here, but more will come out later. The publication 3 is a demonstration system that consolidates the previous two works, but modifies it slightly to include modern day LLMs. So that the notation is clear. I mean, the mapping to the notation is clear. The patient data, once again, is X. Here, there is a new terminology introduced, which is G of X, which is the ontology. I'll show you in a second what that means. C is still the process knowledge. The training is end-to-end differentiable optimization using the stages, composed losses across the multiple stages. This is the picture. So like Megha was asking earlier, this is a patient view, which is a chat conversation. So as much as you can tell from the patient view, the fact that they're engaging long enough, you can measure that using turn-by-turn statistics, multi-turn statistics, is the only indication we have that the patient is satisfied with the text. And as far as the expert is concerned, they see the right-hand side view. So they first see a graph. That's the G of X part, where the text is mapped to ontological elements in the graph. And then they see a potential hypothesis for what's going on in the patient view. That's one. they also see process mappings. So are they depressed? In what way are they depressed? Are they suicidal? In what way are they suicidal? In this particular case, unfortunately, the suicidality is the worst case. So you alert a 911 care provider in that case. That's what we had built into this system. Um, Now, the actual patients, not patients, but synthetic patients that we handled in this case were only mild and moderate depression categories. But then if you're building a realistic system, it has to still be aware of the extreme cases in case it needs to take intermediary action or at least alert an expert. So that's why the suicidality questionnaire is still baked into the system, even though it does not handle extreme cases. It's designed to handle extreme cases. Um, okay. So this was published at AAAI 2023. Um, and the language model used here was the GPT 3.5. Okay. This is another example of the way that you can use the outputs from this system to explain to an expert. So Megha was asking, how do you explain to a end user, in this case, a domain expert? So you can exploit the taxonomic relationships in the knowledge graph, and then you can clearly portray to the expert that these are the concepts that are going on, clinically relevant concepts that are going on from the patient text. You can then map it to elements in the definition to clarify the portrayal. And you can also uh, obtain information like symptoms, right? These are expert curated knowledge graphs. So these are not automatically generated from data-driven methods. So this is a really good output from a domain expert's point of view. From an algorithmic point of view, if you had a graph like this and you tried to implement it in logic, in traditional logic-based formalisms. Earlier, I touched upon what's a sweet spot for logical expressivity versus neural network-based flexibility. This is a clear example of a graph-based formalism winning over a traditional logic-based formalism because you need to trace these paths. If you had cast this into a logic language, a predicate logic language, let's say like Prolog, then you have to do subsumption reasoning that's not efficient for long paths, right? So uh, in our work, a clear trend that emerges as that sweet spot is integrating knowledge graphs with neural network technologies. Mm.
The
Okay.
subsumption reasoning would be not very forgiving. You have to convert all that into this, syntax, because at the end of the day, all of those predicates have to be exactly matching and harmonized. This is where everything breaks down when you want to do everything in a strict logical context. While here we can bring in soft match and approximate and things of that nature that are a lot more practical because of the vagaries and inaccurateness of human language.
Mm-hmm. Mm-hmm. Yeah, and still, even though given what Dr. Seth just elaborated on, um, people are still in doubt about what's the right formalism. So, is it logic based or knowledge graph based? We have done a thorough survey, as I'll come to later, and you can, in objective ways, characterize the advantages of knowledge graph formalisms. Dr. Shet just mentioned several of them. But in logic, you can still retain some advantages, like you can write rules if your knowledge base is in the form of rules. So hopefully we'll get much more clarity on that as I progress in this work. Um, that's one of the future goals, as you will see later. Um, so this is the method that's under review right now, related to Dr. Shet's first question on why don't we just prompt it for conforming to triple structures and checklist structures and any other structure that we want it to conform to, and then use that conformed representation to verbalize later on as a last step. What that entire end-to-end pipeline looks like is as follows. You take the original text, you map it to concepts and definition elements, using a prompt. And then now you can run those mapped concepts through your flowchart, whether that's linear or nonlinear in structure. And you can include that as a constraint set to modify the output that would otherwise have been generated using a direct input feed to the language model. Our preliminary results on this are promising. So hits at 1, meaning compared to the ground truth. We have ground truth not on the textual explanations, but we have ground truth on is the diagnosis correct? Are they depressed or not? Are they suicidal or not? What is the severity of it? Things like that. So at least with respect to that result, the initial numbers are quite promising. In the paper that we've submitted on this across various LLMs, we've evaluated many more things than that. Like, does it actually also match the ground truth explanations? And when the results are out on that, we'll find out. Okay. So then the result summary so far is across the board, without question, you see drastic improvements on the things I mentioned in the proposal statement: accuracy, safety, and explainability. So at least for the medical task. Then going forward, what would we like to do given this preliminary evidence to the promise of this framework? We want to generalize the framework. So formalize a modular system that encompasses generic pipeline stages, process conditions, and records training and inference artifacts. It could record meta aspects of the pipeline, metadata, and other evaluation metrics and other analytics. And to obtain insights on how to best systematize this framework, we so far have conducted 3 types of surveys. What are all the available neurosymbolic AI approaches out there? How have they implemented the dichotomy between discrete logic and continuous neural network-based optimization? We've explored through my work at Bosch. Dr. Oltromari here was my supervisor. Cognitive architectures and their ability to provide the necessary scaffolding for this type of decision making or decision support. And finally, we've surveyed integration of language models with automated planning systems. So to go into a little bit more detail, this is the neurosymbolic AI-based survey, which is broadly categorized into 2 parts. One, where you work with the parameters of the neural network and somehow superimpose a procedure on top of those parameters that distills a graph structure out of it, or a logical structure out of it, a discrete logical structure out of it. Then once you have that, you can directly map it against your knowledge in whatever logical formalism it is, for using classical isomorphism checks, and then conduct decision support that way. The second approach is when you have to take your logical structure and compress it to a vector space. And if it's a graph, there are graph neural networks, for instance, to do that. If it's a logic-based formalism, there are logic tensor networks to do that, and many more emerging almost every day. So those are the broad categories 1 and 2. And within 1, I mentioned you can compress graph-based methods, and they have certain algorithmic features. So they enable large-scale perception, meaning they can scale very well. They enable a reasonable amount of abstraction as afforded by the ontological structure in the knowledge graph. They also enable analogical reasoning because you can map elements in one knowledge graph to elements in another knowledge graph, one from the source domain and one from the target domain in any analogical scenario. You can do planning also. In planning, the role of the knowledge graph is to clarify the domain language and also the steps. You have application level features. So when the end user uses such a system, what do they gain? They gain user explainability, as I've shown examples of in the medical scenario. They gain the ability to specify constraints in a not so difficult manner. I'm cautioning that a little bit because a knowledge graph is still a little bit of a learning curve to a lay person, or maybe at least triples are doable, right? So on the other hand, if you ask them to specify a logic rule as a constraint, that's just too heavy a lift, right? So you also have scalability. Graph reasoning is more scalable than logical theta subsumption. And you have, because you have all this efficiency baked in, you can think about continual learning methods where you revise on the fly, right? So all of these algorithmic level and application level features I've tagged from low, medium to high. And um, this paper presents a comprehensive survey of what is out there. So just one more interesting thing here, maybe I'll touch upon is more recently, you have heard of agentic systems. Maybe you have heard of agentic systems and you've heard of tool calling systems. So here you see an example of that in 2A, the second one, what we're calling federated pipelines. So LangChain is a library that chains together LLM agents. And then at each step in the chain, you can invoke an external solver. So if the chain involves a search tool, for instance, you can invoke Google's SERP API. If the chain involves a math solver, you can invoke Wolfram Alpha, and so on. So that's what's caught on. You'll find most of the conversation in any LLM benchmark today about this type of thing. We've explored cognitive architectures. Here you have this rich theory of cognition that maps to different parts of your brain. And then you have the ultimate goal is to distill the functioning of the brain into a tractable computational procedure with cognitive architectures and also make them well-behaved software artifacts. So all of those bode well for a computational implementation of an intelligent system. So this is a reasonable thing to explore. And so here I've shown directly the mappings between the canonical components of a cognitive architecture called the common model of cognition and what you would normally encounter in AI-related terminologies. So for instance, if we start at perception, your natural language processing tools, computer vision tools would go under perception. And then following perception, you would go into what's known as long-term memory and procedural memory. Those are ontologies, knowledge graphs, how you organize that perceived information into ontological structures and hierarchies. Or how do you organize the steps needed to solve a particular task in any kind of process-related formalism, right? Then finally, you have the working memory, which is at inference time, you have only a limited amount of scratchpad space to work with. It's unreasonable to expect that in the human brain, they use all of their available long-term memory and procedural memory for solving every task at inference time. They only load a subset of it into their working memory. This concept is formally known as bounded rationality. And then you make a decision, right? So, and that decision translates to actions, and you get feedback from the world about whether or not that action was optimal or suboptimal or what degree between those two. And you can revise various components of the system. Finally, we have explored planning and language model integration. So these are the different categories. This is work with Dr. Srivastava's group, and Vishal is the first author. I think he's here. Um, so here you interface with terminology you typically find in planning literature like PDDL, so planning domain description languages. Um, how do you modify plan generation? How do you construct a model that can help you with your domain definitions, the preconditions, actions, postcondition effects, and what are the predicate axioms, influence, and things like that? Um, how do you do multi-agent planning? So planning solvers are pretty mature right now. You can encode a whole bunch of classical algorithms in there, such as A star and other planners. Planners are pretty interactive. So the planner will on its own ask clarifying questions sometimes or generate exceptions. And so it's in, there's a lot of work that looks promising for integrating all the rich body of work available in automated planning literature and language models. as a viable pathway to neurosymbolic AI and process knowledge-based learning and reasoning. Okay, so these are a select list of publications covered in this proposal presentation. Um, and those are the number of citations I've attached there to demonstrate the impact that it has had so far, even though we haven't generalized it across task solutions. And I'll get to that in a second, the reason for the difficulty with that. Um, this is a full list of publications. I've been fortunate enough to have seen considerable success in this line of work. My Google Scholar has the remaining details. This is an organization of it for easier viewing. What are the core computer science related stuff? Um, what is the knowledge representation related stuff? What's process knowledge infusion subjects, cognitive system based subjects, different application scenarios. So in the this proposal, the majority of it was related to medical health, but we have tried some of these methods out in manufacturing, nutrition, and things like that to gain more proof of concept. So what's next for the next 3 or 4 months? So I mentioned that there's a difficulty with assessing this type of framework reliably. It's because if you open up the evaluation framework for any reasoning system today, you find reasoning across these kinds of categories, mathematical reasoning essentially. So ultimately, these are not representative of real world task complexities. So on the right hand side, you see a picture, a depiction of application scenario that we are facing right now with the school behavioral health here at this University of South Carolina. Um, the steps involved there, you build a neural network using domain knowledge. That's just the first step. Then you have to do reasoning of a good number of varieties, so monotonic and non-monotonic reasoning. So the deductive abductive cycle has to be conducted efficiently to be able to support that. It's very different from when you have well-defined axioms and you're doing axiomatic deductive reasoning like in the mathematical case. Um, then you have to do alignment of a more challenging variety. Alignment today is conceptualized as someone prefers a response versus not preferring a slightly modified response. Instead, in the real world, what alignment looks like, or at least in this use case, is that every person has a comprehensive list of duties, the administrators, the staffs, and the counselors, and so on. And alignment for each of them does not have just minor linguistic variations. That's what the datasets contain right now. They have drastic semantic differences. And so alignment needs to be reimagined in a significant way. Instructability means somehow the prompt based instruction is working for many of the things today, but I'm sure all of you have experienced that you shout at your ChatGPT at some point, you prompt it for 10 turns and it still repeats the same mistakes. Um, Even if you're doing relatively pedestrian tasks like coding, you encounter these issues. So instructability for real world task complexity again has to be reimagined so that it actually takes in the prompt that you're giving it and stays consistent in its memory with what you have said. Um, so that's the thing. What are some competing frameworks that are up and coming? So we have from a group at MIT, CSAIL group, a declarative system for optimizing AI workloads. They have recognized many of the issues I just spoke about. And they have a solution, so we will be looking to compare against them. The AutoGen framework is the state-of-the-art LLM-based solution. And then there is Adelflow, which is a prompt optimization framework. So um, the people who run this group, they are of the belief that the prompt is at the core of the issue. So if you can make enough optimizations to the prompt, like we do in prompt engineering manually, then you can solve, at least in part, some of these issues.
I think there's so many fundamental problems. How can the prompt be so precise? We have shown, so many times that, a small change in the prompt will totally change the results. So for anybody to and small change in the you know training would change a lot of things. So there are many moving parts here there where you can't be reliable, you can't consistent or repeat the results. And even for human, the change may be minuscule. For system, the change may be massive. I think we need to capture that.
Hmm. Yeah, yeah. So the moodiness of LLMs at a fundamental level is a huge challenge. And people have really thrown billions of dollars at solving that problem uh, with no success, no measurable success so far. So something needs to change, and hopefully we'll make promising steps towards that thing. Um, okay. So to summarize, we need a general framework for process knowledge infused learning and reasoning, which includes a generic formulation, benchmarking, and task gems that are actually representatives of places where this type of setup is required, um, as opposed to mathematical reasoning. Um, Exploring architectures. So AI systems, if you open a classical AI book like Russell and Norvig, it has some architectures, but then there's cognitive architectures. I covered some of that. So we would need to explore what's available out there for intelligent system design. Then finally, also, of course, we would like to release um, a software package covering all the successful implementations during this exploration. So these are a subset of the collaborators that I've worked with over all these years for all that work. The biggest thanks to my advisor, Dr. Shed. And the funding agencies that have been a part are NSF, of course, and then a UK Innovation Institute at the Alan Turing Institute. And yeah, I think that's it from me.
All right. That was a very nice presentation. It lasted just under an hour. Okay, that were already a few questions. Um, I think that we should have questions um, from anybody really at this point. Oh, Amitava, okay, okay, I see one of the committee members had to leave, but I guess this he explained the situation, so let's not worry about that part. Um, I would like to ask if there are questions from the anyone who's not on the committee first. Let's try that. Mega Chakraborty already asked a question, but maybe you have more, or others may have questions. I noticed there are even people here who are not from USC. I saw Mohammed Ali Javidian is on the call, and I suspect there are some others who are from other places. So I don't know if you have any questions, comments, concerns. Okay. Well, then let's see if there are questions from anybody at all, including committee members for the candidate. It's this is a large body of work. Maybe I will start with a comment. The slides you used today were very different from the slides you sent to the committee. Okay. You sent a document with 16 slides that was very, very concise. There is one thing that was completely missing from the slides you presented today, and it is your proposal for a lambda calculus for uh, uh, your process flow, I think.
Mhm.
It's a typed lambda calculus. I wonder whether you want to say a few words about that.
Yeah.
And maybe you want to tell us why you decided not to have a slide on that. It was is clearly just an initial proposal that you have there. I seem to remember 5 types. correspond. One is a function, and four correspond, I believe, to input, output, and features, or the C's. The maybe. I don't know. Do you want to comment on that a little bit? Why are you interested in that, for example? Yes.
Definitely. So, um, as in the first perspective on the prior work I covered, we saw a whole variety of languages for implementing a process modeling workflow.
Mm-hmm.
The reason I included the lambda calculus in that initial draft is to clarify first what are the computation limits. So, for
Mm-hmm.
example, what are the limits on essentially the Turing machines you could simulate using this language, and how that um, corresponds to process modeling patterns in a generic sense, so that you can then speak in a language agnostic manner that these are the computation limits. You can then type it so that you can give some hints into what are valid implementations of higher order function mappings versus not. And then that really helps with the first step towards implementing parts of this that would be required in a generic framework, like what should be your compiler choice, what should be your language choice, should it be declarative, should it be procedural. um, for instance, at Bosch, during my work at Bosch, we had the pleasure of attending several presentations. They were using languages that look like Haskell. They used a language called WebAssembly for
Mm-hmm.
that's efficient for IoT devices for running on edge computing software. So to get just for myself and for the community at large clarity on what are reasonable formalisms to adopt for a robust implementations. That's why I had included that initially. But I then found that it's kind of difficult to articulate it in its entirety right now, so I left it out.
Yes, I suspect it is. I did notice you mentioned Haskell and WebAssembly now. I don't know WebAssembly, I know Haskell, and I noticed you had left Haskell out from your proposal document. You mentioned Lisp, Julia, and Python, I believe.
Mhm.
And it seems that Haskell should have been mentioned, as
Mhm.
in any list of modern functional languages. Thank you for addressing this. Um, my suggestion, if you want to continue in that line of work, you probably want to discuss this with someone like Dr. Fu, Frank Fu. I don't know if you've ever had the chance, to
Mhm.
he really has technical expertise in this. I see that Ms. Chakraborty has raised her hand, so let's hear the question there.
Thank you, Dr. Valtoda. Kaushik, this question is regarding your work on CSSR, where you were trying to diagnose the patient's depression level. If you can go to that slide in which you showed your proposed implementation, in which so the question is, in the first baseline model that you showed, they had not highlighted the part where it said it's been a hot minute now, which I saw later that in your work you have taken that into consideration, because that talks about the duration of how long the patient has been
Mhm.
suffering for.
This one, this slide.
Yes, this slide, right? So the intention here is that you want to, through this piece of text that the input text that you have, you want to try and answer each of the PHQ-9 questions to determine the level of severity of their depression. Is that right?
Yeah.
So in this case, you were able to find out that, okay, they have made a reference to how long they have been suffering for. It's been a hot minute now, and that is a very abstract way of telling that they have been suffering for over 2 weeks.
Mhm.
So my question is, how were you able to, for each of these input texts, for each line and for each string, you had to understand that, okay, this is referring to a temporal aspect of their depression. So and this representation comes in a very abstract form. It is not clearly stated that we have been suffering for 2 weeks or 3 weeks or for from this date to that date. How were you able to manage the abstract reference of it within a syntactic format that the PHQ-9 requires?
Yeah, so that's a good question. So um, ideally, we would like a representation space that handles that kind of verbal variety in how you express something. But here, the actual solution is a lot simpler, which is that hot minute is in the Urban Dictionary and it corresponds to several weeks. So when you embed those two, you find that there's a temporal aspect to it. Um, but in the general case, hopefully we get to a point where the model actually encodes in its representation space that hot minute could mean the same kind of temporal aspect as several weeks versus 2 weeks, and that would be very interesting. Yeah.
So my follow-up question would then be, instead, if the wording was something like, it's been a while, or it's been a long while since I've been feeling this way, or instead of, a hot minute. So how I completely agree that the encoding of that in a representation format would be helpful. But when you're just parsing through the string and you have these verbal or syntactic abstractions that need to be taken care of, um, that
So
kind of becomes cumbersome to check.
yeah, so the objectives are to lessen the load on the expert and also to err on the side of caution, right? So when you see anything temporal at all, you pick it up. But as long as you have mapped it to something that they can verify instantly, instead of
Mhm.
having to try and you know carefully look at those yellow highlights from the baseline methods, that's already gotten us some of the way there in terms of improving quality of the output. That's the objective here, but definitely I I have a keen interest in a method that could do that reliably. Yeah.
Mm. Right. Okay, thanks.
I also have a question. This is a more general one. This is Tilini. So, from your interactions with domain experts and probably clinicians and patients with depression and these sorts of issues, how do you feel? How do you think that they feel about computer-based, AI-based, or LLM-based solutions? This is just to get to know the general consensus of the field.
Yeah, that's a very pertinent question. So now the general sentiment is fear, right? Because the general sentiment is dominated by language model narratives. And so the general sentiment is these systems are, I mentioned earlier in an informal sense, moody, right? So then you essentially throw them out, right? You can play around with them for some time, but for real world deployment, they just don't work. They don't at all work, right? So that's what's led to the fear sentiment. But the people that specifically worked with us on this, they're much more encouraged that you can actually provide a viable solution to something like this.
So they're looking for clinicians, they're looking at a future where they could use this type of systems to reduce their load and all
To
that.
reduce their load, to do decision support.
Okay.
Because that's the primary issue, that they want reliable decision support, and they want it because the infrastructure is inundated by too many patients and too little care providers.
Okay. So the patients, do they feel like it is easier to talk to this kind of a system, or it's not doing anything for them?
So all they see is that patient view, right? So it's an app.
Okay.
Like if
Okay.
you ever talk to a counseling app, they
Okay.
they're just doing that as
Okay.
far as they can tell. Yeah.
Okay. Okay. Thanks.
Well, if I may follow up, two questions that jump to mind based on the previous two comments and questions by Mr. Chakraborty and Ms. Visirivarden Tilini. One is time. Your formalist does not explicitly include time. You view multi-step decision making as an application of your formalism, not part of it. And I wonder whether you feel that that is a problem for you, in that maybe you need to extend your formalism to deal with time, explicitly, like in, a hidden Markov network, a Markov decision process, a temporal Bayesian network, a dynamic Bayesian network, something like that, should be part of your formalism explicitly. I don't know what you think about that. Maybe I'll stop there for this question.
Yeah, so to sort of preface this, there are two notions of time that is being talked about right now. One is the sequence in which the process happens, the
Yes.
multiple stages. And the other is within each individual stage, there are temporal concepts. In this case, the individual stage going on right now is mapping to the questionnaire. And within that, there is this temporal concept. And then mapping the questionnaire is also itself part of multiple stages that this process goes through. So with those two aspects of temporality in mind, we are definitely going to include in our generic formalism the stage sequential nature explicitly. And about the within individual stages, the temporal aspect, it's very tricky. We'll the suggestions that you mentioned, Dr. Voltert, about the time-based probabilistic graphical models, those are definitely something we would love to try. But a stronger statement than that right now I'm not able to make, but I will definitely try it, yes.
Thank you.
Okay, I think we should try
Well,
and wrap up with the committee mode. Let's go to committee mode, and thank you for all the other people to join. We'll meet again as soon as possible, but let's just have a meeting with the committee and
okay. So, if you're not a member of the committee, please leave the meeting. And thank you for joining. Yes, this made the meeting better.
All right.
Good. So now, again, Dr. Das couldn't stay for the rest of the meeting. He sent a note to me that said that he is very familiar with the work of Kaushik Roy, and he can, basically follow up individually if necessary. But he seemed to indicate a positive attitude, so I think we can take it for that. So now we have the really difficult question for Kaushik. If we want to go that way, I'll start with one, vagueness. Okay, so this always scares me. The linguistic imprecision. Uh, I would like to hear a little bit more about how you deal with that. You mentioned the slang dictionary in one case. You were lucky that the slang dictionary had a pretty clear definition, but you're losing, I wonder how you're dealing with that. Clearly you're not taking a Bayesian approach. You're not looking at uh, utterances as indications of measures, if you like, or of underlying clear concepts, clear variables or clairvoyant variables. So how do you deal with that?
Right. And so from a technical point of view, in one of the slides I had displayed that you take the probabilistic model output, the neural network output, the token probabilities, and you can modify it using several criteria. An unsafe lexicon was part of it, and a knowledge base with an ontological structure was also part of it. So in fact, you can show mathematically that the fixed point to that neural network solution corresponds to the maximum a posteriori estimate, where you to model that in a Bayesian perspective. or the other way around. It's the fixed point to the map solution. I mean, to the posterior distribution corresponds to the optimal parameters for the neural network solution. So you can show that. And we did in one of our earlier works on synthetic domains. So there is a Bayesian formulation in place for modifying token probabilities. That only answers part of the question. That's a technical method, sure, but I think elephant in the room is what should go in that lexicon. And that we have a continuous interactions with the domain expert, and we make sure for them that our algorithmic processes stay efficient, so that when they have a revision, it's not that you have to retrain everything from scratch. You have the method to incorporate that edit in a more efficient manner. That is the two-part answer, with the caveat that there's still a lot of implementation work to be done to properly qualify that answer. Yeah.
So this idea of interpreting probabilistically the output of the neural network has been around for a long time. My worry is that as soon as you allow for natural language expressions, that are inherently vague, you may, yes, have a probability distribution or interpretation, probabilistic interpretation of those expressions, but since they are not clear, you still have you still introduce errors, and that may be maybe something to think about
Definitely.
some more.
And maybe I wasn't entirely clear on that particular point. The lexicon is a bunch of words, but then the knowledge base, the KB in the notation, is an ontology. So you are imposing Bayesian priors at the level of concepts and hierarchies. And so that mitigates a little bit of the issue with linguistic vagueness.
Okay.
Again, there's a lot to be done, but yeah, just to add.
Yeah. We don't maybe that's a meta comment. I don't expect you to solve every difficult problem here. Of course, I think the committee would agree with that. Okay, let's see other questions.
Maybe following up on that topic, right? So I think in your work, I have been lucky enough to see your work over a couple of years as an internet Bosch. So this idea of course, combining deterministic representations with probabilistic ones, with more I would say vague one, if you want. Is you can we cannot assume that you are gonna solve it in your PhD thesis, but I think what it was relevant that you did is always trying to find this trade-off between again vagueness of natural language and precise formulation across different formal languages with different type of expressivity. However, I just wanted to ask you a little bit to comment on this. So we were at the same symposium last year when Ron Brackman, introduced this distinction between knowledge in general and knowledge in use. He was mentioning common sense in that particular example, but of course this applies to domain knowledge or of any kind. So when we infuse knowledge into these data-driven algorithms, we are very good in identifying the boundaries of the knowledge. So the boundaries of the knowledge base. We can choose different type of languages and different type of expressivities, from knowledge graphs to out to ontologies or other type of languages. And then in the process of infusion, then we actually instruct latently, let's say, the large model to actually use that knowledge for some downstream task. And so I think what is not solved there and unclear is how can you guarantee, especially in applications like those that you showed today, right, for mental health, how do you guarantee that this holistic intelligence system use the knowledge that has been infused correctly? So maybe you can comment on that.
That's a Hard question. Yeah, it's a very good question. So guarantees, um, so one of the main reasons that I took a fancy to cognitive architectures when we worked on it, because I think they're fundamentally well-behaved software artifacts. So for instance, guarantees that you would typically be afforded in a CI/CD pipeline where you can write unit tests and you can check various aspects of it. You could do, for instance, in a Actar software. But you could not do that in traditional AI software. But there is a place that we're trying to get to where you can say the neural network is mapping some piece of unstructured text to a concept, and then it you can compose that mapping. So, for instance, if you're trying to map to a chain of concepts, you can make sure that the mapping is the mapping function is following that chain structure as well, instead of mapping individual stages separately and having nothing to do with one another. So, and the way that you can provide certain guarantees on how well that mapping is constructed is to design loss functions and then theoretically analyze the loss function. Um, for instance, you could say that it's a high dimensional mapping, so you can at least say that if you shape the vector space using proper procedures, then you can say between three vectors, two of them are closer than uh, say another pair. And so in that sense, you can write a kind of loose boundary around what's safe or what's not safe. But then when we get to a more narrowed down perspective on top of that, you take that loose boundary and then you try to apply symbolic constraints to say that within problem case scenarios ABC, I'm sure that these symbolic constraints apply. Everything else is an exception that without fail needs to be intervened upon by a human operator, especially in a case, in cases, I mean, in application scenarios similar to the ones I've covered. In the vegan ice cream one, you could still make a case that it might be pretty dangerous, but I intended for that to be a trivial use case. But yeah, so
Fundamentally, you try to take space, symbolic and formal and well-defined uh, knowledge representation and try to shove it in the parameter space, which is inherently probabilistic. There is no way you're going to guarantee that. And that's why, Alessandro, we are also working on, although it is an early stage, a reverse process where we are trying to do knowledge elicitation.
Mhm.
So putting the knowledge into the language model versus extracting from the language model what approximately it thinks. And once we have that, now we are working with much smaller,
Yeah.
the space of parameters is vast, but number of symbols we have to deal with is much smaller, to the extent that you are only working on a specific problem, not, theorem proving. Then you can just address that reasonably efficiently and get the solution out. That doesn't mean that extra elicitation or extraction of the knowledge from parent spec will be perfect either, but then it can be tested. And that is the way we are trying to work on to give other alternative, and we'll have to see which one will work, but I think we have some use cases. And in fact, Vignesh and I have a proposal with Kaushik is intimately involved, that we're supposed to send out this week. We did not, Vignesh, this weekend, man, let's get
Uh-oh.
it up.
No, I think this is a very interesting approach, and I'm actually happy to hear that you're working in that direction. So I think the the most famous approach or implementation of this approach that I know of that recently is from this startup Elemental Cognition by Dave Ferrucci from Watson IBM. They do exactly they do something similar. Right? They use LLMs as a source of knowledge, so knowledge bases, but then they have like a formal system that check all these where basically you infuse you put all this knowledge inside, and then you can actually prove deterministically when you need that type of precision, which can be defense based scenarios, can be health, of course, one of the main reasons why Watson IBM didn't work for health is that they applied right away there